Okay, so we've been kind of focusing on valence bond theory, right?
Yeah.
Now I'm gonna blow your mind. Let's see, let me share my screen. See what you guys remember about valence bond theory. Okay, so remind me, what is this guy?
It's the hybrid shell.
The hybrid shell
forms. It's 2 P's and 1 S, so it makes 3.
Okay. So
available spaces.
What dictates this? What dictates this hybrid shell compared to this hybrid shell?
Was it the bonding of electrons?
It's got more attachments.
The number of attachments. Okay. So let's see, if I have something like this, what would be the orbital? What would be the hybridization of the center atom? Or something like this. Or something like this.
Sorry, what was the question again?
What would be the hybridization of the center atoms?
It'd be for the nitrogen one and be sp3d1, wouldn't it?
Would it be sp3d1?
Would it just
So.
be SP3?
That is correct. It would be
Is it-
sp3. Yep.
It's
That's
just
4
the-
attachments. 1, 2, 3, 4. 4 orbitals. 1, and then 3 p's.
Oh.
You got that? You see it?
Oh, I counted the nitrogen, that's why.
Yeah. Okay. What about the carbon here? Right here.
Bonds count as 1, right? So the double bond, that's just 1 attachment.
That is right. That is only
So
1
then-
attachment.
It would just be the sp2. Or yes. Whew.
That's right. sp2. That is correct. Okay. And then we know that the first bond, the double bond, is going to be a pi bond. This one would be a sigma, so then that would be incorporated in that sp, and then the pi bond would be the other. That's why we don't count it. Okay, what about here? The last with CO2.
Is that just
SP1 or SP?
Yeah, the same thing with the medium.
Okay, piece of cake, not too hard.
Yeah.
Okay, so when we talk about valence, stop sharing. Actually, let me start sharing. Sharing something different. Let's see. You see my blue waters? So when we talk about valence bond theory, right? So that's what you guys just learned was valence bond theory. Now that is dealing with the hybridization of the orbitals. Okay. So it also, we're talking about those sigma and pi bonds. Okay. And then we're kind of using the molecular shape to kind of predict the hybridization. Does that make sense?
Yeah.
Okay, the electron pair geometry to predict the hybridization. Okay, and we also know that resonance structures aren't going to have a factor in this. Okay, so when we talk, we're going to learn molecular orbital theory. Now, molecular orbital theory is going to be a little bit different. We are going to implement some of the things that we talked about, the pi and sigma bonds, but I'm also going to introduce you to the concept of antibonds. Okay, so we have, when we look at things, right? So do you guys remember when we were talking about waves?
Mm-hmm.
When we were talking about wave theory? Okay, so in a sense, we're going to be kind of using aspects of wave theory here as well, too. So if two waves are in phase, right? Meaning that they both have the same frequency and they kind of overlap. So then those waves become additive. It adds on. But if two waves are destructive, right, or out of phase, then they're going to cancel each other out. Okay, so let me show you what I'm talking about. Do you guys see my screen?
Yeah.
Okay, good. It's one of those mornings. Okay, so here we have in phase, right? So they have the same frequency, they're overlapping completely. So those guys are going to be additive. So it's just going to be like adding on to that wave. So that amplitude is going to just get bigger, and then the wave is going to continue, right? Where if it's destructive, right, or if it's out of phase, then these guys are going to cancel each other out. You have one that's going up when the other one's going down. So when you take some of them, it's just going to be a flat line. Does that make sense?
Yeah.
Okay. So when we're talking about bonding, bonding could occur the same way. Now, let me kind of elaborate. These are two independent theories to try to explain the difficulty of advanced bonding, right? Try to understand what is really going on, right? These are theories that are being floated around, okay? So these are your two independent theories. They have some similarities, but they're going to be things that are going to be quite different between the two, okay? So one is additive or constructive, and one is destructive, okay? So one is going to amplify, one is going to basically minimize, subtract, okay? So the additive one is going to be considered your bonding. And then I'll kind of explain to you how it pertains to bonding. And then this guy is going to be like your antibonding. Okay. Okay, so here we have two S's that are coming together, right? So if they come together and they're in phase, it's going to be an additive one. So then you're going to get bonding. So then we'll have what we call sigma S, right? But we have the possibility of these guys not being in phase. In other words, the electrons are not in phase with each other. And if they're not in phase with each other, then they're not going to come together. They're going to actually repel each other. And then that's going to be like that destructive interference. So constructive, destructive. Okay? If they're in phase, they come together, they form a nice bonding orbital. If they're out of phase, they're going to repel each other. Okay? Are you with me so far?
Yeah.
Okay. So if we look at it, we think about it because it's all about electrons, right? So again, if those electrons are in phase with each other, they're going to have a force that is going to cause them to come together. So you guys remember the electrons have spin associated with it. So if that one is going one spin, right? And then one is going the other spin, right? So those are going to be positive forces. They're going to come together because then they can form in opposite directions. They're going to bond. But if one is going one spin and one is going one spin and they try to come together, right? Those spins produce that force that pushes them away from you. Okay? By them having those opposite spins, it allows them to come together. So are you with me?
Yep.
Okay. So in the case of pi bonds, I mean not pi bonds, p orbitals, the same concept. If they're in phase, they're able to come together. So then this guy would be called, because it's a sigma bond, it's a sigma px. If they're out of phase, meaning that we have the blue over here and the red over here, then they can't come together because they're sort of like the same type of spin. And so as a result of that, since they're the same type of spin, if we look at the whole thing, same type of spin, same type of spin, they're not going to come together. They're going to push each other away from each other. Does that make sense? One spin would be like our up spin. This guy would be our down spin. So then they're able to come together. These guys are kind of like having two up spins. Okay? Kind of. No, I can't hear you again. I think you're on mute. It says you're muted. Who muted Cassie? Can you now talk? Nope, can't hear you now. Are you adding your question to the chat? Okay. I'll give you a second. So anyone else? Everybody else kind of got the understanding? You see how this works?
Yeah.
Okay. Now the same thing is going to be able to happen with those pi bonds. So it's going to happen with single bonds, and we're going to have pi bonds that are going to be able to do the same thing. So if these guys are side to side, and if they're so if they don't orient the correct way, if they're not in phase, then you're going to get repulsion. If they're side to side and they orient the correct way, you're going to get fusion. Okay, if they're in phase. Okay, out of phase, in phase. Destructive, constructive.
Can you
Okay,
hear me now?
I can hear you now.
Okay, so what I was asking before my computer was retarded, it's like the electrical forces, like when they attract each other.
Yeah.
So if they would obviously push themselves away if they were the same, kind of like
Yeah,
same
Yeah.
kind of concept.
yeah.
Okay.
Now the thing is that, and we'll get to that. We'll start talking about it. We should really start talking about it in a little more depth. But that's essentially it, right? So if they're in phase, they're going to be able to merge and come together. But if they're out of phase, then they're going to stay apart. Okay, so let's see. So predict the type, if any, of molecular orbital would result from the adding the wave function so that each pair of orbitals show overlap. The orbitals are all similar in energy. Okay, so the first one, A. What's going to happen in that situation? Is that in phase or is it out of phase? Is that going to be a bond forming, or is it going to be an anti-bond? Is it going to be a sigma bond, or is it going to be a pi bond?
They're out of phase, right?
Aren't they
Or-
in phase because they're the same?
Or no, they're in phase, yeah.
Okay, so the first one is in phase, right? So because you have, well, they're opposite of each other. You have red over here, blue here. You have blue here, you have red here. So the blues are able to overlap with each other. Okay, so this guy is in phase. So what type of bond would that be?
That was the omega, no. Sigma S, right?
So it's a sigma. So it'll be a sigma 3. I have to draw it because sigma 3p x. Okay, so that would be a sigma 3px, and it would be bonding, right? And the way that we signify anti-bonding, we put a star on it. So this guy means anti-bonding. Anti-bonding. Okay, what about this guy?
Out of phase.
Yeah, this is way out of phase, right? So we have, well, we have this guy, and then we have this guy, and they're not even overlapping correctly. So ultimately, these guys are going to kind of cancel each other out. The only way that anything could happen is if these guys realigned. So in terms of you have one in the X direction and you have one in the P direction, right? They would have to realign each other to do correction, right? So this guy is going to result in nothing, right? So there will be no result. So if they realign, in other words, one of these guys moves to the correct orbital, if this guy went up, then that guy would actually be out of phase, right? Okay, what about this guy?
That's out of phase, right?
This one is out of phase. So this guy would it be a sigma or a pi bond? If it could form a bond, would it be a sigma or a pi?
Pi.
So this guy would be considered your pi anti-bonding, meaning that it's not going to bond, they're going to kind of push each other away. But it serves as like what we call an orbital. So you have, when we start looking at it, we have sigma, we have a sigma, then we'll have a sigma anti-bonding. Then we'll have pi, pi, and then pi anti-bonding. And so I'll kind of show you what I mean in terms of energy levels. And it's going to be based upon energy, right? Let me go clear. Okay. So here we're going to label the orbital shown as either sigma or pi, bonding or anti-bonding. So is this a bonding or anti-bonding? The way it looks.
Be anti, because they're
Yes. That is correct. So this guy is anti-bonding. Sigma, is it a sigma anti-bonding?
Wouldn't it be pi at that point?
I don't know. You think it's pi?
No. Oh, that.
Because what do we know about pies? What does pi look like? A pi bond.
Two different points, kind of more
Yeah,
than
so
one point.
it's overlap
Yeah.
like this, right? These guys are going to be, if they overlap, they would overlap end to end, right? So we know that anytime it's end to end, it's sigma. So this would be a sigma anti-bonding. Okay, and it also kind of tells you, right? Because then the electrons are being pushed to the other side. That's why you have that little orbital there, and it's pushing the other guy in the other direction. So that means that the electron is spending more time on this side than on that side. Okay? Does that make sense?
Mm-hmm.
Yeah.
Does it make sense, Selena? Sadie, Matt?
I have a question. Oh,
Never mind.
Oh, you can go, Abby. Sorry.
how would, sorry. How like do we? What's an easier way to identify like when it's pi bonding and when it's not pi bonding, when it's sigma bonding, when it's not sigma bonding?
Okay, so really the images are just trying to give you an idea. So they're just kind of representing whether it's going to be in phase or out of phase. There's going to be an energy scale that's going to be associated with the electron. If we take a look at it like this, right? So when you're doing overlap, if the two colors are the same right next to each other, right? When they're in the case of a sigma bond,
Yeah.
then that's going to be bonding. If the colors are opposite, if it's red here, blue here, and then red here and blue here, then that's going to be anti-bond, right? Because then that represents these guys going, well, in the same orientation. So that means that the electron moving in that same orientation as that guy. So you have them kind of spinning in the same way. So these guys are not going to overlap. They're going to actually repel each other since they're in the same way. When we think about electrons coming together, we have one that's going in one spin and the other spin. That's how they fit in those orbitals, right? And that's the way that they're maintained. But if they're going in the same direction, then they're not fitting in the same orbital. So here, since you have these guys, these two colors next to each other, right? Or if we had the reds next to each other, then that means that they're gonna be in phase, right? So they're gonna be able to come together. Okay, does that make sense?
Yeah.
Okay, now in the same thing with the pies. So when the colors are in the same orientation, right? They're in phase with each other. Do you get what I'm saying? So if I had, yeah, so if I had red up here, up top here, and blue down here, they're gonna be in phase with each other. Okay, but so pies, I guess if we look at it, pi is going to be a little bit different. So, but all it is that you're able to bring those colors together. In the case of the pi, the same thing. You're able to bring the colors that are alike together.
Okay, that makes more sense. Okay. Thank you.
So if you look at the anti-bonding,
Yeah.
right, look at the orientation, right? We have red, we have blue, we have red, we have blue, right? So any way that I put this, if I put this guy over here, they're never going to have the same colors that are going to be able to come together, right? Because here in the middle, we have red and blue. They're opposite. They're not going to come together. Okay, so this basically means that the electron is orbiting in the same direction. So it's all going in the exact same spin. So same spin, right? And so as a result of that, these guys put off this force that are the same type of force. And so they're going to repel each other rather than being attracted to each other. Does that make sense?
Yeah, that made more sense.
Okay, Selena,
Yes.
you had a question?
What do you mean by when the electrons are in phase or out of phase? Like, do you mean whether they're spinning in the same direction or in the opposite direction?
Yes, that's what I mean by in phase and out of phase. So
okay.
they're considered to be in phase with each other if they're spinning in those opposite directions, right? So then they're able to come together. They're going to be attracted to each other. And then it's going to be an additive type effect. But if they're out of phase with each other, then they're not going to want to bond. And then that means that they won't come together. They're going to be pushing each other apart. Does that make sense?
Okay. Yes.
Okay. So I can't remember. So this guy actually had done the crystallization of the HIV protease, right? And he actually has spent a long time actually doing it. He was actually one of my close friends' bosses when he was at the NIH. So part of crystallization is actually playing on this theory, and he kind of pushed the molecular bond theory, right? Because based upon that, that's sort of how he was able to manage the crystallization of the HIV protease, which before nobody else had been able to sit there and do it. I'm sorry, the molecular orbital theory, sorry. And so this is just the HIV protease, and this is just showing you where there's actually a drug that was actually targeting the protease itself. So this is the drug on the inside. This is the actual protease. That would be the structure. So crystallization is one of the most difficult, particular protein crystallization, one of the most difficult fields to do. And he solely based it upon the molecular orbital theory and just that concept of the energy associated with it. And it just so happened that it worked. And so that's part of the reason why, you know, people like this theory compared to the valence electron theory, is because in the case of crystallization, it works pretty well. But the valence electron theory works well for other situations when we're talking about like chemicals only. Although protein is a form of a chemical, but it's a little bit different in the sense because it's that biological molecule that is going to be constantly moving like other molecules, but the way it's moving is going to be on a, we'll say, a four ways of moving, right? So for instance, when we talk about proteins, they have what we call, I can't even think of it. They have 4 types of structures, right? So you have your primary structure, which is just the order of the sequence of the amino acids. You have your secondary structure, which is just basically kind of your folding of the amino acids, just basic folding. Then we have our tertiary structure, which is like folding of regions into each other. And then we have our quaternary structure when you have subunits of proteins, right? So here, these are basically 2 proteins that are coming together as different subunits. And so that plays a part in how that molecule is going to behave and how it's going to fold and how it's going to move, okay? And so it adds a whole nother layer to it. And because that whole other layer, molecular orbital theory did a better job of explaining what is needed to get the structure of that molecule. And by them being able to crystallize the structure, particularly in the context of the drug, it actually added quite a bit of information, and it kind of revolutionized the developments in the HIV drug therapies, so, or pharmaceutical areas. Okay, so let's start talking about the molecular orbital energy, right? So this is the energy diagram for the molecular orbital theory, right? Okay, so now you're gonna have to bear with me. There are gonna be, and I'm gonna say this for 2 reasons. One, I'm a little rusty myself, right? And 2, there are gonna be points where this guy changes, right? So there is points within the organization or within molecules that we're looking at that we're going to have a flip occur. And I'll talk about that a little bit more. So, damn it, I think I missed the slide. Hold on. Give me 1 second. Yes, I did. Did we talk about this slide?
I don't
No.
think so.
Okay, so let me talk about this real quick. So remember at the very beginning of the chapter, we were talking about oxygen being suspended, liquid oxygen being suspended between a magnet where nitrogen will flow right through.
Yeah.
Okay, so this is the chapter where we actually start looking at that. So if we look at liquid nitrogen, molecular formula for liquid nitrogen is N2. The molecular formula for liquid oxygen is N2, right? So O2 is paramagnetic. You guys remember what paramagnetic means?
Yep.
Okay. So paramagnetic basically means that if we put it between 2 magnets, it's going to get stuck. That's 2 magnets. Diamagnetic means that all the electrons are all paired up, so it won't be able to get stuck and it'll flow right through. Okay. O2 is paramagnetic, where N2 is not paramagnetic. Now, N2, there's a point where we look at that nitrogen. Nitrogen, remember I told you it's a little bit of an oddball. If you guys kind of look at trends like size, if you look at electron affinity, if you look at nitrogen, kind of is a little blip. it gets out of order compared to some of the other guys. Have you guys noticed that about nitrogen? Let's see.
I think you mentioned it, yeah.
I can't remember what I mentioned in one class or the other. That's the problem when you have so like 20 million classes. It all phases together. It all becomes in phase, right? It's funny when you could just put one letter and it pops up almost automatically. Okay, so let's look at, we'll do electron affinity. Okay, so if you look at the trend, right, here's the electron affinity. And then you come over here, it goes up, and then nitrogen drops down, and then it goes back up. You see that?
Yeah.
Okay, let's look at ionization energy. Okay, here it goes up, it goes up, it goes up, and then it goes up way too much, and then it drops down under oxygen, and then it goes back up, right? So again, nitrogen is that little bit of an oddball. It causes that really upbeat in the case of ionization energy, and then it drops back down, okay? So let's look at, where are we? What was the other? Radius. Okay, let's look at the radius. Okay, so gets smaller, gets smaller, gets smaller, gets smaller. Well, actually, that one does behave right. Get smaller, get smaller. Okay, so then here, this one is pretty good. This one worked out pretty well. Can't remember. There's another one. Electron affinity or electron negativity. Oh, well, I can't remember. There's another one that it does exactly the same thing. So it wasn't radius, it wasn't and it wasn't affinity. But nitrogen is this little oddball, right? So what is it about nitrogen that makes it a little bit of an oddball? If we look at nitrogen and we do our pairing, nitrogen has 3 electrons in the p orbital. When those electrons go in, they are going to be going in the same orientation. Where in the case of oxygen, it's coming back with that 1, right? Kind of leaving these 2 guys open. Does that make sense? So nitrogen, this is nitrogen, this is oxygen. Okay, so when we look at these guys, right? This guy here kind of throws things off. Having that other electron, it kind of throws things off. These guys are definitely oriented. These guys kind of form a balance because according to Hund's rule, you guys remember Hund's rule? Yes, no, maybe?
Kind of.
Okay,
Yeah.
so Hund's rule,
You have to fill each level before you go back and fill
Yeah.
the next.
yeah. Hund's rule says you have to fill each level before you go back to fill the next, right? Okay, so nitrogen goes through and it fills each level. It doesn't do this. Okay, it doesn't do that. It actually will go through and fill each one first. And the fact that you have an electron in each one of these gives it a little more stability than it would in the case of, say, oxygen, which has this one filled, but then these 2 guys are kind of free on their own. Does that make sense? Are you with me so far?
Yep.
Okay, so this is actually going to also serve as a switch between the 2, how the molecular orbital theory is going to behave, okay? And I'm going to talk about that here. Hold on, where are we? Okay, so here's an example if we're doing BE, and in this case, this is going to be E2 plus. Okay, so if we look at this guy, one of the things that we're going to determine is whether these guys are actually going to form a bond or they're not going to form a bond. Okay, so if it ends up in that anti-bonding region, more than likely you're not going to get a bond. So there's certain things that will form bonds, will form, in this case, a homonuclear diatomic, right? So basically meaning that it's going to have two nuclei, and then your electrons are going to be around it, so it's going to form a diatomic together, right? So we know that BE, first off, BE2 does not exist, right? As a diatomic. BE normally is just BE, because we know our diatomics, right? By nature. Good, okay. Okay, so if we go through, and first if we do BE, so this is going to represent the atomic orbital, so this is just for one BE. So we know that BE has two valence electrons, is that correct?
Yep.
Yes.
So this is what it's going to look like for each of the BEs. So when they come together for that molecular orbital, we have what we call sigma 2 sigma anti 2s. This is sigma 2s, sigma anti 2s. So and then that one is just a normal, right? So this is your bonding, this is your anti-bonding, okay? Now, so what's going to happen in this context is that then you're just going to put an electron from here in here, and an electron from here in here. And so they're going to have to be oriented a certain way, right? So in a case like this, if we end up in an anti area, an anti-bond, then these guys aren't going to form a true bond. So you're not going to have the existence of your BE, right? Your BE2. So that guy won't exist in nature. So it won't actually bond. It won't exist. Does that make sense? Okay, because we ended up, so in this case, we ended up, if it ended up here, like say, let's start with hydrogen, to be clear. Okay, hydrogen has, scratch this. Hydrogen has how many electrons?
One.
So let's go. So hydrogen has one valence electron. Okay, so if we have hydrogen, then we'll put in that guy. So we have its sigma bonding. Okay, so this guy is able to form a diatomic atom, H2, where beryllium it has a bonding and an anti-bond, right? So you have your bonding and your anti-bonding shells. Then in this context, it's not going to be able to form a stable B2 molecule because we ended in our anti-bond.
So this is just like your roadmap to determine if
If these guys are going to exist in terms of they're going to come together and form a nice molecular bond. They're going to form a molecule. So we know that B2 is not going to come together and form a molecule. Does that make sense? Okay. Has the ability. So in this context, we have the same thing in terms of, in one case, we have our two valence electrons, and this guy is lost one, Be2 plus, right? So it ends up in our anti-bonding state. And then we're not able to sit there and get bonding. So it won't be strong enough to maintain a bond, okay? So Now let's talk about bond order. Okay, so bond order identifies the net contribution of electrons to bond strength, right? So if it's a bond order of 1, it's going to be a single bond. If it's a bond order of 2, it's going to be a double bond. If it's a bond order of 3, it's going to be a triple bond, right? So the way that you calculate your bond order is the number of bonding electrons minus the number of antibonding electrons, and then you divide that by 2, okay? So if your bonding order is 0, then a bond won't form. Okay, so let's go with hydrogen. Okay, how many bonding electrons do we have?
1.
1. So we're talking about for the molecule itself.
What's diatomic? So sorry, there's 2.
Okay, so we have 2 minus antibonding. Do we have any electrons here?
No.
And we divide that by 2. That's going to be a bond order of 1. So it's going to form 1 single bond. You get it?
Yeah.
Okay. Okay, so when we're talking about that beryllium, we have 2 bonding minus 2 antibonding. Divide that by 2, that equals
0.
does that
Yeah,
equal 0?
okay.
Right? So that tells us that we won't form a bond. Does that make sense?
Mm-hmm.
Okay, so really easy. These guys are going to basically balance them out. You're going to end up in that anti-bonding region. So you're not going to form a bond. So you're not going to form a stable molecule. Where in the case of the hydrogen, we were able to form a stable molecule. We had a single bond there. Okay, so what if we do helium? We want to see if helium is going to form a diatomic. Okay, so what am I going to do? How do I calculate if the bond order?
So would it be
2.
8?
Okay, so we have 2. I heard 2.
Oh,
Take away. This is kind of the part where I'm still a little bit lost on the anti-bonding.
How many? How many are in here? In the anti-bonding. So this is the bonding. So sigma without a star is bonding. Sigma with the star is anti-bonding.
Okay, so 1.
So how many do you have here?
2.
2. So it's 2. You just count the number of electrons that are there. So it's 2 minus 2 over 2. What does that equal?
0.
Okay. So the bond order of this is 0, which means that this guy would not be stable. It would not form a stable molecule. Okay. Nice way of looking at it. This is, both of these are the 1s, right? So in the case of that 1s, then if you end up in this region, you're not going to form a stable molecule. So if I had a half, right? Can we have a half of a bond? You can have a half of a bond? So you're telling me I can give you 1 electron and this guy don't give me any, and they're going to share that 1 electron between the two of them.
I was thinking of the quantum number. No, you can't have half.
No, you can't have a
Sorry.
half, right? So if you have a half, you also know that that's not going to form a bond. What if I have, say, 2.5? You're on mute again, Cassie.
I'm talking to myself.
Okay.
I was saying you'd have 2, but you can't because of the half. So
Yeah. But in that context, you would have a number that is greater than 1 or 1 or greater, right? But
huh?
I said you would have a number that's technically greater than 1, right?
Oh,
But
when
you'd
you
still,
do, yeah.
yeah. So, but the thing is that in that context, you can't have that half a bond, right? So that's going to cause something to be unstable. Okay, probably means there's a mistake. Okay, questions, concerns, Cash? I
Dr.
see
Henry,
somebody in chat. Okay, yes.
is this diagram, would you only use it for diatomic molecules, or can you use them for
Good
anything
question.
else?
So you actually can use it for diatomic molecules as well as hetero or 2 different compounds, right? So we can use it for molecules, and we can use it for, I guess we can use it for molecules in general and for compounds. But you have to be aware of the atoms that you're using in the context, because there's a point where we have a switch in those energy levels. Okay, and I'm going to show you that with the diatomics. Okay, and so then they're going to behave a little bit differently. Okay, are you with me?
Yes, so
Yeah.
far.
Yeah, it's a mess, but it's cleaner with the diatomics because it makes more sense. It's more logical with the diatomics. But when we start getting to those compounds, it becomes a lot more complicated. Okay.
So for the antibonding, is that what that little asterisk means? Is that what that
Yeah.
represents?
Yes. Yeah, the little star thing, the asterisk, it means antibonding. So if
Okay.
you have pi star, that means it's antibonding pi bond. Okay. Everybody else, are you guys with me? Good questions. I like clarity. Sorry if I didn't say that earlier. Okay, so here's the energy levels, right? And so we can see for the different diatomics, and this is basically showing you the energy level for each of the diatomics. You'll notice, okay, so here, the energy level for, and this tells you what they are. So these guys are the anti-bonding pi bonds. So that's your XY pi, and this is your anti-bonding sigma, okay? So you'll have sigma, sigma, so sigma bonding, sigma anti-bonding. Then you'll have sigma 2p or p bonding, pi bonding, pi bonding, pi anti-bonding, pi anti-bonding, and this guy is sigma bond, right? So if you take a look right here between nitrogen and oxygen is when we have a flip, okay? So between that nitrogen and oxygen, we flip the sigma bonding with the pi bonding. So we get pi bonding first here, and then we switch to sigma bonding first. So all of these guys, they go pi bonding first, then they go sigma bonding. Do you see that?
One more time, please.
What was that?
One more time, please.
Yeah. So if you look between the oxygen and the nitrogen and oxygen, right? This guy represents the sigma 2p x, and this guy represents these guys here. These guys represent the pi 2p y 2p z, right? So these guys, they actually flip in terms of energy level. So this sigma 2px drops below the pi's 2pxy, Y and 2pxz. Okay, in terms of energy level. So in other words, we would feel if we go filling up the electrons, we'd go and fill up these guys first, and then we'd fill up these guys in the pi first before we fill up that sigma. But in the case of oxygen, it works just the opposite. We fill up the sigma before we fill up those pi's. Yeah, that look, Cassie.
I just got it. I see what you're saying now.
Okay, so in other words, we're just moving this guy in a lower, it's lower in energy for O2, and then anything beyond that. So between nitrogen and oxygen, we flip the energy level. This energy level drops down. It's actually lower. So it's going to be beneath those guys. Okay. So if we talk about anything that's above oxygen, so in terms of our diatomics, any of the diatomics above oxygen are going to have it so that their sigma is lower than their pi. So let me show you on the next slide. It'll help maybe a little bit. Okay. So if we look at this guy, right, in terms of energy levels, this guy the sigma is higher in energy level than the pi's. Okay. Ah, come on. Now it's not behaving. Okay. So nitrogen, sigma is higher. Nitrogen and lower, sigma is higher than pi. But oxygen and higher, sigma is lower than pi. Okay, are you with me? So when we fill it up, right, let's say, how many valence electrons does oxygen have?
6.
It has 6. Okay, so we have 1, 2, 3, 4, 5, 6. I know I did that all wrong. You can spank me later. Okay, and then so okay, so when we fill these guys up, it's going to take 1 from here, 1 from here, 1 from here, 1 from here. Okay, so then that takes care of the 4 that's down here. And then it will take 1 here, 1 here, 1 here, 1 here, 1 here, 1 here, and 1 and 1. Is that right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Did I mess up? 1, 2, 3, 4, 5, 6. No, I didn't mess up. I just didn't. Is that right? 1, 2, 3, 4, 5. Oh, there's 8. Hold on. Okay. So in this case, if we go bonding minus antibonding, divided by 2. Okay, how many bonding do I have?
2, 4, 6, 8, 10.
Okay, so I have 2, 4, 6, 8 bonding, right? Because these guys are antibonding. So,
Oh, there's an asterisk on it. Sorry, I can't see.
sorry, I know the image sucks. So these are all bonding right here in red. So that's 8. And then my antibonding?
2, 4.
4. When I divide that by 2, My bond order is,
2,
okay, am I gonna form a bond? If
6.
so, what type of bond?
Double
Double
bond?
bond.
A double bond, right? Okay, so now nitrogen. Nitrogen uses this scale. It doesn't use this scale, okay? So then in the case of nitrogen, we have 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so if we fill these guys up, okay, so bonding order,
Is there 6?
there's 2, 4, 6, 8, bonding
Mm,
and antibonding. Any antibonding?
4.
Where do you get 4? Look for the asterisk.
I'm trying. That's right. 2's right there.
2.
All right, my
The
bad.
asterisks are right here. My bad. I'll work on those images there. Okay, so these guys have asterisks up here. Can you guys see the asterisks?
A little bit, yeah.
Okay, so we got to work on that. We'll make them bolder or something. Okay, so then, and we divide that by 2. So then that's 6 divided by 2.
Tree.
Okay, what type of bond?
Triple.
Triple bond. Okay. Okay, so now because of that switch, right? So these guys actually end up in alone, right? Unpaired, right? And so remember when we were talking about what is the word? Diamagnetic versus paramagnetic.
Yeah.
Right? So this guy, para, is paramagnetic because you have these 2 electrons that are free by themselves, where all of the nitrogens, the nitrogen molecule is together. They're all paired up. So this guy is diamagnetic, and this is para in terms of the molecule. Does that make sense?
Yeah.
Okay. Because of this, right?
So your bond order is always only going to be 1, 2, or 3?
Yes, because you can't have more than 3 bonds. Having a 4th bond is unstable. It's totally unstable. So let's say we were talking about carbon. Which energy shell would we use? We use this one here, or would we use this one if we're talking about carbon? We wanted to look at carbon.
It'd be the nitrogen one, right? Because you
That's
said
right.
it was after oxygen.
Okay, so let's go ahead and do for carbon. We have one less electron, valence electron. Okay, so then everything else would be the same down here. 1, 2, 3, 4. Okay, let's see, is that right? 4, 4. So okay, so how many bonding?
4 or 6? 6.
How many
Okay.
anti-bonding?
2.
Wow, so we can form a C2, right? And how many bonds would that be?
2.
Okay. Make sense? Yes, no, maybe?
Could we do
Yeah.
another example? Because like I feel like all the electrons are all over the place for me.
Okay. Okay, so let's do fluorine. F2. So which energy shall we use? A, call this one A, and we'll call this one B.
B, right?
Let's go back to our little cheat sheet on the other slide. Maybe. There we go. Okay, fluorine is after oxygen, right? So we're going to be using the one where the sigma is below the pi. So, oops, A or B? Where is sigma below the pi's?
A.
A. Okay, so we're going to be using A. So let's go ahead. How many valence electrons does fluorine have? This
7.
represents fluorine, a single fluorine atom. So it has 7. 1, 2, 3, 4, 5, 6, 7. Okay, this guy, same thing. Okay, and this here is going to represent our F2. Okay, so we go ahead and we fill them in. That's 1 from this guy, 1 from that guy, 1 from this guy, 1 for that guy, 1 from this guy, 1 for that guy, 1 from this guy, 1 from that guy, 1 from this guy, 1 from that guy, 1 for this guy, 1 from that guy. Let's see, 1, 2, 3, 4. Okay. So bonding. How many bonding?
10.
1, 2, 3, 4. So that's 2, 4, 6, 8. Because remember, it goes bonding, anti-bonding. These guys are going to be a little bit different. They're going to go bonding, 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 and then anti-bonding, anti-bonding, anti-bonding. So you have your bonding first. Okay. So you're using those upper energy, the higher energy are anti-bonding. Doesn't that make sense that it's higher in energy? Because you're trying to put together something that doesn't want to come together. Okay, so it's gonna be more energy associated with that than compared to the bonding. So we have 8, 8. Okay, so then bonding, I have 8, and then anti-bonding, I have what?
6.
6. Okay, so divide that by 2. What does that equal?
0.
8 minus 6.
Oh, 1.
Okay, you guys are worrying me here. Okay, so is it going to form a bond?
Yeah, single bond.
It's going to be a single bond. Is that true? Do we know about fluorine? Isn't fluorine one of our diatomics? Have no fear of ice cold beer.
Yep.
Okay. Questions, concerns, Josh?
So outside of the diagram, you fill up like the valence electrons, right? And then in the centers, when you kind of combine them to see where they land or something like that.
Yeah. So no, the center represents the molecule. The outside represents each atom. So this is the atom, just fluorine. The middle represents the molecule. So molecular
okay.
orbital theory. So it represents the molecule.
Okay.
Does that make sense?
Yeah.
Yes.
Okay, so in theory, you could actually do mix, right? But your mix is going to be sort of dependent on, well, it's going to be dependent on your molecules. Like, so for instance, if I have carbon or an oxygen, right? So my mix is going to be sort of dependent on that, you know, it's like, so carbon and oxygen, CO, right? So in that case, which one would you use? Because we have that in between the two, right? So if we go ahead and we put carbon here and oxygen here. So valence electrons.
Four for carbon.
And then how many for oxygen?
6.
6.
Okay. So then okay. Okay, so in this context, is that right? 1, 2, 3, 4, 5, 6, 2. I think I got carried away. Okay. So if we have this guy, bonding, minus anti-bonding, divided by 2. How many bonding?
8.
Anti-bonding?
2.
3. Triple bond.
Okay. And so, and if we'd done it the other way, it'll actually work out exactly the same value. It could be a triple bond, right? Because we're not getting a shift between those antibonds. But in terms of how it pairs up, that's going to play a part, you know. Does that make sense?
Kind of. I'm getting it though.
Okay. So when we talk about insulators and conductors, right? So we're also talking about what we call these, it's called band gaps, okay? So like an insulator basically has, here you have, excuse me, what we call our valence band, we have our band gap, and then we have our conduction band, okay? So in terms of energy, we're thinking about this in terms of energy. So our valence band is going to be lower in energy than our conduction band. And depending on what we're working with, insulators are going to have a huge band gap. So it takes a lot of energy to get from the point of just having valence to conduction, right? So because of that, you have that gap in between. And so that those energy levels are huge to get to that point. And so you're not able to do that, so you're not able to conduct. Okay, so semiconductive material has a smaller band gap. The energy gap between those two are a little bit, it's a little bit, right? So they're able to conduct just a little. So relative speaking, huge gap between the two, less of a gap. A conductor, right, metals and stuff, those guys aren't going to have a huge energy gap. So there's not going to be a lot of gap between the ability of it taking from that valence point to the conductive point. Okay, now all of that has to do with that bond order, okay, or not bond orbital theory, right? So if things are closer together in those energy levels between, you know, the different the P's and the things like that. So if we take a look, hold on. Okay, so right now, so these are metals, right? Over here, lithium and stuff like that. And we know that we're not going to really have an Li2 molecule or anything to that extent. That guy isn't going to exist. It's only going to be existing as lithium. But if we go through and we look at this energy level, and we'll notice that the gaps of the energy level, there's pretty decent gaps between the energy of those bonding and the anti-bonding. So what we're looking at is the gaps between those energy levels to determine whether something is going to be conductive or non-conductive. So those gaps are going to close for things that are going to be more able to conduct. So you're going to, those valence electrons, and in terms of the molecule itself, you're going to have a smaller gaps associated with it. So like when we look at this, so this represents the atoms themselves. This is going to represent the molecule, right? So things that are conductive is going to have a smaller energy gap associated with it. Things that are semiconductive is going to have a medium-sized energy gap, and things that are not conductive that are insulators are going to have a large gap. Does that make sense?
Kind of, yeah.
So we're looking at that energy, the energy. So it takes more energy to go from that valence to the conductive because you have a big gap between the two. Okay. Semiconductor, you have a smaller gap between the two from going to valence to conductive. A conductive material, you have no gap between the two.
Oh, okay.
Okay. So here is that oxygen. We've done it already, so we're kind of ahead of the game. But you guys can see you have these guys that are unpaired, and then that's what makes it paramagnetic. Okay, so that's the reason why it sits between two magnets. It'll stand in suspension if you pour it over two magnets. Okay, or between two magnets. Questions, concerns, cash, credit. Okay, so we're going to stop here. 4 minutes early. We're doing great things. I will see you guys in a week and a half, roughly.